Okay, great. So welcome to the last but not least talk of the day. I'm happy to welcome Francesco Zappa Nardelli. He's an associate professor in RIA. And Francesco has done a lot of interesting work in semantics and weak memory models, actually very influential work. But today he will tell us about something different. So go ahead.
Yeah, thanks, Martin. So something Martin didn't tell you is that usually my talks on weak memory models ended up being very depressing. So I'll try to do something different for once. So debugging debug. This stems from conversation and work with Stephen Kell with at Computer Lab at Cambridge. So I start from something everybody knows. And then I try to be more grandiose. So, yeah, this happens. We are all used to get segmentation faults. So, and we are also used to have this reaction. Let's ask for a backtrace so that we can actually debug. And so we get some function names and we get some addresses. And we know that these addresses corresponds to something in memory. Okay, so the first one is just the instruction pointer, and then the blue and the red actually corresponds to the return addresses which have been pushed on the stack. Okay? Now, imagine that you have the call stack in memory, and the only thing you know about it is the top of the stack. You only know the stack pointer. How can you generate a backtrace? Okay, you must be able to unwind the stack to find all the return addresses. So, question, given a call stack, is there a reliable and efficient way to produce a backtrace? Okay? And of course there is one answer, which is called DWARF Unwinding Tables. And this is something that lives inside your binary. You can inspect those, and they're quite boring when you learn how to read them, because basically this tells that for each instruction identified by the instruction pointer, the instruction address, it gives you an expression. So this is a return address. So this says if you are executing instruction at 4004F1, then you want to compute where the return address is stored, then take the stack pointer, add 56, and subtract 8. Magic. And it does this for every single instruction in your binary. And additionally, it also tells you all the places where all the call save registers have been saved, so that if you have to do real stack unwinding, you know how to go back to a decent state. So these tables are relied upon to implement stack unwinding. But who does have to rely on this? Well, obviously, GDB, debuggers, but also pretty much every single program analysis tool. I mean, a common one, you have a sampling-based profiler. It has to stop the program, and it has to inspect the stack to decide which are all the functions which are active right now. And to do that, yes, to be able to unwind the stack. And something more unexpected is that the C++ runtime actually needs these tables to implement exceptions. Why? Because, well, to implement an exception, it has to unwind the stack and call all the destructors of all the objects which might have been pushed on the stack. So, wait 1 second. The runtime of a programming language is looking into something which is called debug information for it just to run. Be scary. So the first thing you should take away from this talk is that debug tables are not only for debugging. Okay? They are really useful. Point number 2, where do these live? Okay, this is the structure of an ELF binary. Now, well, we know that there is code, here there is a symbol table, statically allocated variable, some stuff to implement relocation, and in the middle somewhere, there is this AH frame table that contains the dwarf unwinding tables. Now, if we zoom on a binary, then this is what we'll get. And it doesn't look like the tables that the table that I showed you before. So what's going on? So how can we interpret this? Very easy. We go back to the standard, DWARF debugging information format version 4, freely accessible, okay. And it explains how to party stuff. Okay, it is a bit weird format, but yeah, parsable. And do we get the tables? No. We get this. What do we have this here? This is bytecode instructions, advanced lock, compute expression, do something else. And what do we have? We have expressions that can refer to registers, like stack pointer, instruction pointer, do some comparison, do some other logical operation. And all this bytecode is actually interpreted on demand to reconstruct the table whenever you need unwinding. And what you have, you didn't know, but you have, is that you have a Turing-complete stack-based machine which can dereference memory and access all the values in my machine registers in a place where I'm sure you didn't expect it. Okay? Now, why is this fun? First, because this is badly specified. Okay, there is a standard, but don't believe the standard. So all this was introduced because GCC had to implement exceptions, so they defined their own format, which is called H-frame. Then DWARF came and said, we should standardize this stuff. This is actually useful for debuggers and all the rest. So they defined their own format, debug frame. And guess what? The two are similar, but not quite the same. And if this one is well defined, the AH frame one is basically specified by GDB code or GCC code. And the best description I could find is this blog entry by Jan Lance Taylor. Okay, so badly specified. What else? It is a burden for the compiler to generate. Why? Because each compiler pass is actually generating code for two different machines, the processor and the DWARF unwinding machine. Okay? Maybe you try to compile something and ask, give me the assembly, gcc-s, foo.c, and what do you get? You get the assembly. You can try on your machine, but you also get something weird, this .cfi instructions, and these are actually the instructions for the DWARF unwinding machine. It is a bytecode. And each optimization pass must keep the two in sync. Quite a lot of work that is added to an already complex piece of code. What else? Now, if you're into security, this is a potential vector for arbitrary code execution. You just put a Trojan inside the DWARF, debug stuff, and nobody will notice. And it is actually quite hard to come up with a real attack because there is not so much that you can do. You can read the memory and you can jump somewhere else. But it is actually hard to find a way to jump to your code. But it was done by Olem Ratus in workshop for an offensive technique 11, part of Usenix. So, in general, all this is complex, buggy, and untested. How buggy and how untested and how complex? Well, Linus Torvalds can explain us. So we can ask him, why doesn't the Linux kernel rely on DWARF tables and insist on compiling with a base pointer? So wasting one register, even if you're on IS32, which has some cost. And the answer is in an email that he sent to the kernel mailing list, and he says, let's read it because it is informative. Sorry, but last time we tried, it was too painful. The whole and only point of unwinders is to make debugging easy when a bug occurs. But the DWARF unwinder add bugs itself, or our DWARF information add bugs, and in either case, it actually turned several trivial bugs into a total undebuggable hell. Now, Mr. Torvalds is a reasonable man, so he leaves a door open, gives us a way to convince him. And the email ends with, if you can mathematically prove that the unwinder is correct, even in the presence of bogus and actively incorrect unwinding information, and never ever follows a bad pointer, I reconsider. So what we'll try now is to sketch a way to make Mr. Torvalds reconsider. So, validation of unwinding tables. Let's try to understand what's in this table. It is not rocket science, it is very simple. So let's take some assembly. Well, expect you're familiar with push and move. Push is on the stack. So this is typical Prolog. It saves all the collisive registers and does some computation, allocates on the stack, frees the stack, restores all the collisive register, and goes on. And let's make one assumption. Let's assume that the H-frame table has been generated by the compiler. This happens by default if you don't do anything special. And I also assume that I have an interpreter of the H-frame bytecode that can generate the readable table. Okay? So we have the lovely table. Let's try to understand how the two work together. We know that when we enter into the foo function, the return address is stored at the location pointed by the stack pointer. This is just calling convention on x86. Okay? And guess what? This says, yeah, take the stack pointer, adds 8, and subtract 8. Fine. Then after one push, what happens? It happens that the stack pointer has been decremented by 8. And so, guess what? Our information tells us, yeah, now you have to do the stack pointer plus 16 minus 8. So plus 8. Yeah, makes sense. Yeah. Not so complicated. Now we have another push, so we go to RSP plus 24 minus 8. And then we have a move that doesn't modify the stack pointer or anything that appears in these expressions. So nothing changes. The return address is still stored at RSP plus 16. So I believe that by now you can see how this goes. Okay? And you can remark that the unwinding table is actually completely redundant with respect to the binary code. It is completely defined by the binary code. And it captures some abstract execution of the code. Okay? So let's try to understand this a bit better. Let's take one random line of our program, okay, like this one. And suppose that we know that in an execution, the return address is stored somewhere, 1158, and the stack pointer points somewhere. We can take this expression, and we can do the math. We can take the stack pointer, do plus 160 minus 8, and guess what? We get exactly this value. Okay? So what the remark is that if we evaluate the entry of this table on the current register values, the value for RSP, then we should compute the concrete address of where the return address has been stored. Okay? Now, this gives us a very simple strategy to validate the tables. What can we do? Well, we keep an abstract state, which is a stack of concrete addresses where the return addresses are stored. And we have an abstract instruction semantics in which we just have to trace call and ret, and call push the content of the stack pointer on the top of the abstract state, and pops 1. Ret pops 1. Okay? And for each instruction that we come executing, we evaluate the return address each frame entry for the given instruction pointer, and we compare with the value that we stored in the abstract state. Okay? Now, I'm lying a little bit. There is, to find the location of the collisive register, we have to do some kung fu, but it will do for now. So what we can do is to implement a very simple tool, which has one simple goal, which is validate EH frame entries along just one execution path. Okay? And how can we implement this? Well, we take GDB to do step-by-step binary execution and to give us access to processor state and to give us independence from the architecture for free. And then, well, since you can script GDB in Python, you're stuck with Python. And we write in Python something that can parse ELF and DWARF binary code. And there is a nice library that can partially do this stuff already. We write an evaluator of DWARF expression, and then we script GDB to implement this very simple analysis. Okay? Before you ask how slow this is going to be, GDB plus Python, well, we can process a few thousand of assembly instructions per second, which is not ideal, but good enough, good to do some real experiments. So let's take this code. It was found by csmith plus creduce plus ehframecheck. And this is perfectly defined C code. It is a kind of code that compilers do not like too much because they see lots of loops, they start optimizing it, and then you have complex optimization that fires, and you don't know if, you are in the complex optimization branch of the compiler, and it is where problems might happen. And so you give this to C-lang, pretty much every version in the last 4 years. And what you get this code. So let's try to do the validation of the tables. We know GDB tells us that the abstract state at the beginning is 1000, and it tells us that the stack pointer points to the same location. It is what happens when you enter into a new function. And here we can validate. 100 plus 8 minus 8 is 00. OK, works. Next extraction, push has moved RSP. Abstract state is unchanged. And yes, it works because this plus 16 minus 8 gives the abstract state. And goes on. We get to the pop. Here, everything works as well. Trust me. And then you get the next instruction where pop modified the stack pointer. It added 8. But the compiler didn't update this correctly in the EH frame table, okay? And here we have the tool that says, problem. For fun, all this happens at -0, -2, -OS, but not at -01, and so you might start wondering why. And it is just a coincidence. It is that at -01, the register B is not saved on the stack, so the table is correct by chance. Yes? This is C-lang, and so the last one does this, but many older ones have the very same problem. So, second point that you should take back home is that validation of unwinding tables is actually not that difficult and effective. Okay? Now, if there is any LLVM developer in the room, then I have one task for you. Please fix this one so that we can go on finding bugs. Okay, let's go on. The sad truth. Generating H-frame is a burner for the compiler. Some compilers do not generate H-frame at all. Okay, I can give you some examples. OCaml added the H-frame generation last year, but it was not done by Xavier. It was done by Jane Street because they wanted to run binary profilers on the OCaml generated code. Okay, Haskell has the same problem. OSPOT, you have the just-in-time compiler. It will generate some assembly. You get bugs there. Try to debug that. You get some assembly with absolutely no debug information. You cannot even obtain a stack trace. You have to do some kung fu to do some debugging here. And another problem. Now you're writing some low-level code, so you write some inline assembly in your code. Does all this mean that I should write manually the unwinding instruction in my really complicated inline assembly? And the answer is yes, you have to. Okay, and it can be quite complicated. I have this nice example that comes from glibc, low-level lock.h. Okay, what goes on? Here there are a bunch of macros that implement different locking mechanisms. And the person tried to write some macros so that to reuse the unwinding stuff. And here it is clearly a programmer that knows what he's doing. So this is a code written in a comment that he had to encode manually inside so that inline assembly can put the right byte into the memory. So the person here really knows what he does. And despite this, there is a off by one offset error. And that can result in, if you put a breakpoint in a special place and you ask a backtrace, not something too evil happens, but you get a stack frames that get duplicated. Okay, now if you have some tool or your runtime that is relying on this information, well, it will expect you have twice the same stack frame, and bad things will happen. And again, good luck debugging that. So what we can do, we have seen that validating the table is really simple. Okay, maybe we can synthesize them. Okay, and can we do this? The answer is yes. So we know we have a precondition. When we enter a function, this is called the canonical frame address, the CFA. It is by convention the address of the stack pointer when the call is executed. And it is used to compress the table, essentially. You have seen all the addresses of the register, of the collisive register, are mostly invariant during the execution of the program. So using just one column to modify and avoid the relative addresses to that simplifies that. But we know that, anyway, upon entering a function, canonical frame address is stack pointer -8, because call pushed the return address. And the return address is stored at CFA +8. And now we can check the semantics of each instruction in each basic block. And we have to distinguish a few cases. Okay, either RBP is being used as base pointer or RSP has been modified. Whenever we identify this, we can update the computation of the canonical frame address accordingly. And then it is not too hard to chain all these informations across basic blocks. And whenever you have a loop, we live in a wonderful world where for all this to work, you must have the stack pointer that points to the very same address at the beginning of each basic block on which you loop. So you have two cases. Either it is really the same and you get an immediate fixed point. You don't have to do any fancy analysis. Or the stack frame, it is a loop that increases the size of the stack frame. But in that case, the compiler will have used a base pointer, even if you specified I don't want a base pointer. So we lived in the perfect of the world. Again, there is some extra complexity to trace the addresses of the collisive register, but I'll be honest, implementing this, I have to say that the main difficulty is a tool to work with x86 and power binaries. Okay, so which is the road forward? Yeah, first, we should fuzzy test all the DWARF interpreters. There are at least 4, and it is a good thing that there are 4, because I do believe that they use the fact that there are the redundant implementations so that as soon one fails on something, they can use the other to do checking, and I mean, it is system. And this is how you get reliability. And then we can validate unwinding tables against binary code, or we can even synthesize them. And by doing this, we can identify bugs in generation of tables. If you are into security, you can prevent code injection attacks. And what is probably the most useful, you can make unwinding tables available to other systems, like your hotspot code exploded, and now you generate the table on demand, and you can now launch your debugger and try to understand what goes on. I'd like to conclude with some wider horizons. What else do we have in this very mysterious debug tables? Well, one probably you expect. It is called debug line. It is used to synchronize source and object code. So you have, you know, for each line number, file name, line number, and actually column number as well, unless the compiler is very lazy, as in this case, you know to which instruction this corresponds. Okay? So we have a reasonably precise correspondence between assembly instruction and points in the source code. Okay? And more interestingly, there is another table, which is a debug type table, which gives us a model of data type. What does this mean? So this is written too small. Let's zoom. Here we know that we have a variable z, which is actually a parameter of some function. We know where this is stored. It says that it is stored at the frame buffer register -16. And if by any chance, due to spilling and reloading or other fancy stuff, the location of the variable changes, you will get a table like for unwinding information. For each IP address, you will have a precise information on how to recompute where the variable is stored. And then we know at type, we have to follow the pointer, 7c, 7c. We know that it is a pointer of int. Okay, let's rearrange all these informations, okay? And let's suppose that all these tables are correct. Well, by combining informations in different tables, point number 1, we have precise metadata about computation at runtime, and we can relate source and machine code. So if we can do this, Then we might have precise provenance informations. The people next door to my office do avionic code, compilers for avionic code, and they have to bother with being able to have traceability. So provenance information might be super important. We might be ambitious and do translation validation for existing C compilers, okay? And using the metadata about computation at runtime, we can extract, for instance, we have to rearrange the information, but it's possible to obtain type information for all stack and register allocated variables. And a few things, magical things we might do with this. We know we might scan the stack, and we might obtain the type of all the values which are stored in the registers and on the stack. If you are compiling your high-level language to C and you have to implement a GC, maybe you might use this to recompute precisely the roots of your values without having to prevent other compiler optimizations. We might even do maybe runtime type checking for C. Okay, now, at this point, I believe that all of you are as skeptical as Mr. Torvalds. Okay, no, none of this is possible. We played with a debugger and none of this will work. But I'd like to conclude the talk with a super cool example about what the state of the art of this. So if we take runtime type checking for C, now let's take this code. This code comes from JIT, okay? What you use to store your papers and your code, okay? And there is something that if this object has one field that has this tag, then let's cross our fingers, let's cast it to something, and then let's actually commit the patch, okay? Now you can imagine that this might go super wrong because nothing guarantees that if object type is object commit, you have the right structure to do the cast, okay? And what will happen, you will discover this much, much later when Git crashes. So it would be super cool if we could check at runtime that iObj is really a struct commit. Okay? And by using information in the debug tables, Stephen Kell, Uppsala 16, has been able to do exactly this with some lovely properties. It doesn't have to modify the binary, so you keep binary compatibility. You don't have to add any annotation to the source file, so it is what I call source compatible. It gets reasonable performance, on average 10% slowdown, which is perfectly fine if you're doing debug, not for production, but this is for debugging, okay? And it is not C-specific because none of this debug information is specific to C. It can be used for any languages. So to conclude, I showed you something that maybe you didn't know, that is really at the heart of our computing infrastructure, which is poorly specified and badly designed. It is pervaded by subtle bugs. It is mostly ignored, with a couple of exceptions, by the research community. And it is not understood by most programmers, just like on Stack Overflow. And my point is that the potential of this is largely unexploited, which I prefer to see in a positive way, as there is some exciting research to come. Thank you.
Okay, questions?
Show again the latest code, please. Okay, this is a Git you mentioned, right?
Yeah.
Is this meant to be C or C++ code?
Yeah.
Is it C or C++?
I should ask Stephen, to be honest. I took it from the paper, right?
Okay, I'll just explain why I'm asking this question, because this is a C-type cast, and in C++ you could use dynamic cast, and which will do exactly this.
Okay, I expect this to be C.
Yeah. So can this verification you mentioned point out exactly this observation I'm doing now?
Say it again, sorry.
Because when you, in the next slide, you show these four
properties.
yes. So can these four properties actually come up with this observation saying, look, you could be using dynamically cast here instead?
I mean, what Stephen is doing, I mean, if you start doing dynamic, I mean, so okay, so all this is C code. Remark number 2, you want to use this on arbitrary code. You don't want to rewrite the source of your program just to be able to enable this, okay? And imagine you have legacy systems that you still want to debug, okay? And what Stephen can do using debug information, because in the debug information, you have exactly you can trace all the type of all the allocations, because when you do the malloc, you know what you are allocating, and you can keep this information, and then you can go back to the pointer using the debug table stuff. And, and yeah, you get it for free on code that already exists, without having to change the runtime or change anything.
So what's the next step with this work? Formalization, or like, what are you thinking?
I'd like to get the synthesis to really work. So it is a brand new project started 3 months ago, basically, when you asked me to talk here and wanted to come with something new. So getting the synthesis to work and putting it in practice on real inline assembly. I mean, put all this stuff inside, inside a compiler would be definitely the next step.
Okay, great. So let's thank Francesco again.